Hello and welcome back, everyone. Let's dive into another exciting session as we uncover the revolutionary impact of AI. In the last podcast, we understood from the book, The Fourth Industrial Revolution and 100 Years of AI, the challenges of making AI systems explainable, interpretable, and trustworthy, while highlighting the trade-offs between accuracy and transparency. The book also emphasizes the limitations of current AI in causation, fairness, and ethics due to their reliance on nonlinear algorithms and varying human beliefs. Today, we're going behind the scenes to uncover a hidden truth. Today, we're tackling something that often gets overlooked in the AI world, the constant need for upkeep. And buckle up, because you might be surprised to learn just how much work goes into maintaining and improving the accuracy of AI systems. In this podcast, we'll explore the hidden complexities of AI systems, from maintenance costs to evolving challenges. Keeping AI systems running smoothly can be a real headache, and it can also hurt your wallet.
Yeah, it's kind of like buying a fancy sports car. The initial purchase, it's a big expense, but then there's all the other costs. You've got maintenance, specialized parts, premium fuel, and AI. It can be surprisingly similar. Businesses are often caught off guard by all those hidden costs.
So you're saying that AI isn't like a set-it-and-forget-it kind of technology?
Right? There's this big misconception out there that once you build an AI system, it just hums along happily ever after. But the reality is, AI needs constant care and feeding. It's prone to what we call selective amnesia. It's where changes in the data or the task at hand can make it forget what it previously learned.
So it's like when you train a dog to sit, and then you bring home a new puppy, and suddenly the older dog forgets the command and all the excitement.
That's a great analogy. And just like with retraining a dog, fixing AI amnesia means going back to basics, gathering new data, and teaching the system all over again. And that's where the costs start to add up. Traditional software development uses what's called software DevOps, a continuous cycle of improvements and updates. But with AI, you're essentially redoing the entire development pipeline, from data collection and labeling to model training and deployment, whenever that AI's performance dips.
That sounds way more complex than just patching up some code. How does this retraining process actually translate into costs for businesses? Can you give me some specifics?
So think about it this way. Let's say you built an AI system to detect fraudulent transactions for a bank. Initially, it worked well, but as new types of fraud emerge, the AI starts missing things. To stay effective, you need to continuously feed it new data on these emerging fraud patterns. And that means paying analysts to gather and label those new examples, which can get expensive fast. And it's not just analysts. You need specialized engineers to manage the AI infrastructure, data scientists to fine-tune the models, and even legal experts to make sure everything's compliant with regulations.
Okay, so we're talking about some serious cash here. Are there any real-world examples of companies being caught off guard by these costs?
Oh, plenty. A 2019 Accenture survey of 1,500 C-suite executives found that a staggering 76% struggled to scale their AI projects and get a return on their investment. And get this, Redmond and Davenport suggested budgeting $100 for deployment and support for every dollar spent developing the algorithm in MIT Sloan Management Review.
Wait, 100-fold increase? That's a massive gap. No wonder so many AI projects never make it off the ground.
Exactly. A 2022 Gartner survey revealed that almost half of AI projects never become operational. That's pretty sobering. Really highlights the critical need for understanding the true cost of AI. Alright, so before we get too deep in the financial weeds, let's go back to that AI amnesia concept. It's like the AI is selectively forgetting what it previously learned. This is where the CACE principle comes into play. It stands for changes anything, changes everything. It was coined way back in 2015 by researchers who were studying AI systems. Basically, it means that even small changes to an AI system can have ripple effects throughout its performance. And that's why maintaining AI is such a complex and costly endeavor. You're constantly trying to strike a balance between improving accuracy in one area and potentially sacrificing it in another.
So if maintaining AI is so tricky and expensive, why are we even bothering? What's the ultimate goal of all this effort?
Accuracy. It's that simple. The more accurate an AI system is, the less human intervention it needs. Imagine a world where AI can flawlessly detect fraudulent transactions, diagnose diseases with pinpoint precision, or personalize education to each student's needs. That's the potential we're striving for.
But how do we even measure this accuracy thing? It's not like grading a test, right?
Right. It's not that straightforward. Measuring AI accuracy depends on the task and the type of data involved. But let's look at binary classification as an example, where the AI has to choose between two options, like deciding if an email is spam or not.
Okay, so how do we measure accuracy in that scenario?
So there's more than one way to measure accuracy, and it depends on what's most important for the task at hand. Absolutely. Sometimes there are trade-offs between precision and recall. So precision is about how accurate the guesses were, and recall is about how many of the true answers were managed to be found. In fraud detection, you might prioritize high recall, even if it means sacrificing some precision. It's better to flag a few legitimate transactions than to miss a fraudulent one.
This is really making me think about all the AI systems we interact with every day, and how their accuracy or lack thereof really affects our lives in big and small ways.
It's a fascinating and evolving landscape, and what we have uncovered so far is just the tip of the iceberg.
It's true. We often picture AI as this set-it-and-forget-it technology, but the reality is far more dynamic. Now, we'll understand from the book why you should assume any AI system is outdated within 6 months, unless there's a solid plan in place to keep it fresh.
Wow. 6 months. That's a great point. So where do we even begin with this? The book keeps mentioning how quote-unquote brittle AI can be.
Yes.
What exactly does that mean?
Brittleness refers to the sensitivity of AI systems to even the smallest changes in their input. Think about those passport photos where the lighting casts a shadow and suddenly the facial recognition software thinks your eyes are closed.
Oh, yeah.
And boom, rejected. That's AI brittleness in action.
Oh, it's happened to me before. So frustrating. Is that a common issue?
More common than you'd think. The source states that nearly 20% of passport photos are rejected by facial recognition software due to this kind of misinterpretation.
Wow.
And it's not just limited to facial recognition. Self-driving cars, for instance, rely on AI to interpret their surroundings, but things like unexpected weather, glare on the road, or even a detour can throw the whole system off. These are complex systems operating in a complex world, and that inherent complexity demands constant attention.
Okay, so that makes sense why AI needs maintenance.
Yes.
But what are the situations that trigger the need for adjustments or updates?
One major scenario is what's called data distribution shifts. Imagine you have an AI trained to recognize different types of trees in a lush tropical rainforest. Then you take that same AI and drop it into the middle of the arid Arizona desert. The AI is suddenly bombarded with data that looks nothing like what it was trained on. The lighting is different. The types of trees are different. Even the colors are different. The result is a confused AI and a lot of inaccurate predictions.
Yeah, that's a pretty drastic example.
It is.
What about more subtle data shifts? Does the book give any real-world examples of that?
It does. There's an interesting example about an AI system designed to detect pedestrians, but it was primarily trained on data from areas without snowfall. When deployed in a region with snow, the AI struggled to differentiate between pedestrians bundled up in winter clothing and snowdrifts or other objects.
Oh, interesting. So the change in environment, even something as common as snow, created a data distribution shift that the AI wasn't prepared for.
Precisely. And in this case, simply tweaking the existing AI wouldn't have been enough. The developers had to collect new data from snowy environments and essentially retrain the AI from scratch using a combined dataset. This brings up another important point. These updates aren't always quick fixes. Sometimes they require significant overhauls of the entire AI pipeline, which can be a time-consuming and resource-intensive process.
I'm starting to get a real sense of the dynamism involved in AI development and why maintenance is so crucial. But data distribution shifts are just one piece of the puzzle, right? What else can make an AI system go haywire?
Another challenge that might surprise you stems from seemingly small errors in data labeling. This is especially relevant in supervised learning where humans label the data used to train the AI. Let's say you're training an AI to differentiate between images of cats and dogs. Seems simple enough?
Totally. But I have a feeling there's a catch.
There is. What if, even with the best intentions, someone accidentally labels a picture of a fluffy dog as a cat? Now the AI is learning from flawed data, and that error will ripple through the entire system, potentially leading to misclassifications down the line. And when you consider the massive scale of data used to train these systems, even a small percentage of labeling errors can have a huge impact.
So it's not just about having a lot of data, it's about the quality and accuracy of that data. Every single data point matters.
Exactly. It's like a domino effect. One seemingly insignificant labeling error can topple the whole system.
Wow, this is fascinating. So we've got data distribution shifts and labeling errors. What other landmines do AI developers have to navigate?
The third scenario is a bit more nuanced. Sometimes it's not the data itself that changes, but rather the goals or objectives of the AI system.
Interesting.
Here we use the example of a bank using AI to assess loan applications. Imagine the bank decides to adjust its lending criteria.
So perhaps becoming more lenient in certain situations.
Interesting. So the data might be the same, but the rules of the game have changed.
Precisely. The AI, which was initially trained on a specific set of criteria, is suddenly outdated. It might need to be retrained to reflect the new lending guidelines, which could involve adjusting decision thresholds or even modifying the entire model. It highlights a crucial point. AI systems aren't static entities.
Right.
They need to adapt to changing circumstances, just like any other business process.
That's a great point. And this constant need for adaptation really underscores the importance of ongoing maintenance. It's not just about fixing things when they break. It's about proactively anticipating and responding to change.
Absolutely. And there's one final scenario we should touch on, which is driven by external forces rather than changes within the data or the AI system itself. That's government regulations.
The legal landscape for AI is constantly evolving, and new regulations often require developers to go back and redesign their systems to ensure compliance. For example, a new regulation might mandate a certain level of transparency in the AI's decision-making process.
So an AI system that was perfectly acceptable a year ago might suddenly be out of compliance.
Exactly. And that could necessitate significant changes from relabeling data to incorporating new fairness metrics into the model. This highlights the intersection of technology and policy. AI developers can't just focus on the technical aspects. They need to be aware of the evolving regulatory landscape and adapt their systems accordingly.
That adds another layer of complexity to the whole AI maintenance equation.
Yes, it does.
It's fascinating, but also a bit daunting. But even once you've addressed all of these scenarios, the data shifts, the labeling errors, the regulatory changes, there's still another challenge lurking in the shadows.
There is. And it's a silent but persistent threat to the accuracy of any AI system. We call it model decay.
Model decay. That sounds ominous.
It kind of is. It boils down to the fact that the world is constantly changing. And as the world changes, so does the data that feeds our AI systems. This is known as data drift. And it's one of the biggest headaches in AI maintenance.
Can you give me a real-world example of how this data drift might play out?
Think about the impact of the COVID-19 pandemic. Suddenly, people's behaviors changed drastically, from shopping habits to travel patterns to the way we worked. This generated a wave of new data that looked nothing like the pre-pandemic data that many AI systems were trained on.
Oh, wow. So an AI that was making accurate predictions in 2019 might have been completely thrown off by the events of 2020.
Exactly. And even without major global events like a pandemic, data drift happens gradually all the time. The way we use language evolves, fashion trends change, new technologies emerge. Everything around us is in constant flux, and our data reflects that flux.
So how do AI developers even begin to keep up with this constant state of change?
That's where the concept of MLOps comes into play.
MLOps? Tell me more.
MLOps stands for Machine Learning Operations. It's essentially a set of practices for developing, deploying, and maintaining AI systems in a way that accounts for this dynamism we've been talking about. It's like the secret sauce that keeps those AI engines running smoothly, even as the world around them is changing.
Okay. That makes sense.
Yeah.
But how does MLOps actually work in practice? What are the key elements involved?
MLOps is often broken down into 3 core subprocesses: data ops, model ops, and MLDevOps. Okay? Think of them as the three pillars that support the entire AI lifecycle, from initial data collection to ongoing model maintenance.
3 pillars. That's a helpful way to visualize it. Let's discuss these in detail in the next podcast.
Sure, but before that, let's quickly recap what we've learned today. The podcast discussed AI's high maintenance costs, challenges like data shifts, labeling errors, and evolving goals, emphasizing the need for ongoing updates to ensure accuracy and scalability. We learned that maintaining AI requires constant vigilance and adaptation to changing data and goals, and the key to success lies in continuous monitoring and refinement.
Oh yeah, this knowledge is going to be so critical for individuals, for businesses, and society as a whole to harness AI's power. And for our listeners, if there's one thing to take away from this deep dive, it's this. Never stop questioning. Ask how AI systems work, how they are maintained, what data they use, and what potential biases might be kind of embedded in them. Informed skepticism is crucial in this age of AI.
It's been awesome exploring the often overlooked world of AI maintenance. Looking forward to delving deeper into the concepts of MLOps in the next podcast. Till then, goodbye listeners, take care.